Yeah.
Okay, very good. So last time I explained to you about these relative entropy methods. Okay, so how do you set the scene for these a priori bounds that I was mentioning. So, and then so now what I want to do today is to explain you how you can now prove a CLT out of it. So, as I told you, so the stationary state, okay, of the reaction diffusion model has a well-defined density, because just from hydrodynamic limits, it's more or less easy to show that the empirical measure under the stationary state is concentrated on stationary solutions of the hydrodynamic equation. And if the stationary solution is unique, then we have a convergence theorem. Okay. But if you want to characterize in a more precise way the stationary state, you want to look at more detailed information, like, for example, the CLT, okay, central limit theorem. Before doing that, I want to present a result which is a result which is an strengthened of the what I presented last time of this hydrodynamic limit, something that we call quantitative hydrodynamics. Okay, so when in the classical theory of hydrodynamic limits, so you have this, you have interacting particle systems. These interacting particle systems, that they have some, they are models for some physically relevant PDE, and you want to prove that the density of particles or the energy or whatever other thermodynamic macroscopic variable you are modeling converge to the solution of a certain PDE, which we call the hydrodynamic equation. And this convergence is convergence in law. So in particular, it's a qualitative convergence. It's not quantitative in the sense that we don't really have speed of convergence, because it's just convergence in law, and as usual with the functional limit theorems and probability, at some point you use some compactness argument, and that's it. You lose any control of the speed of convergence or whatever you do. Okay, so now what I want to show to you now is that the entropy, the relative entropy between the stationary state and the product measure with the same density is bounded. Of course, it's bounded because there are just two finite, there are two measures defined in a finite state space. So what we are interested in is the growth of this function with n. Okay, so so let me define a parameter which is useful, which is this GDN. So GDN is the order of magnitude of the Green's function on the terms. Okay, so we will probably know that in dimensions 1 and 2, the Green function on the infinite lattice is not well defined, at least in the sense of limits of occupation time, because the random walk is recurrent. You can nevertheless define it in a renormalized way. But in the for example, if you take the square, lattice of size n, and you kill your work at the boundaries, or if you take the infinite lattice and you kill your work with some rate. There are various ways on which you can make the green function well defined, and in the torus, of course, it's recurrent, but you can also do it. We normalize it and see what is the. And a classical question is, what is the size of the Green's function at the origin in those cases? And it turns out that in dimensions 1 and 2, where the random walk is recurrent, what you get is that the Green's function is of order n in dimension 1, and the Green's function is of order log n in dimension 2. So that's this constant GDN that I'm defining. It's just the Green's function at the origin of a random walk, let's say killed at distance n from the origin. And the theorem, what we can prove, and I have to stress it's a perturbative result because it doesn't hold for any lambda. Remember that our process has it has actually 3 parameters. No, there is a gamma on the rate exchange of the exclusion process that I put when I defined the generator last time. I didn't put it in the first day. There is there is an A and lambda on the reaction rates. Okay, so the A was this thing that we call the immigration rate. On this, if when you interpret this this reaction rate as an epidemics model, as a disease model, for example, and the lambda was the infection rate. So if this infection rate is small enough, then our result holds true. And this is reminiscent of what happens, for example, with the contact process. In the contact process, you also have different behaviors if the infection rate is small or large. So, and the theorem is that if this parameter lambda is small enough, and it depends in some way on A, B, and so A is the immigration rate, the D is the dimension, and gamma is the, let's say, the diffusion coefficient of the exclusion part. And so if lambda is small in absolute value, then this lambda 0 theorem is true. And what we can prove is that the entropy grows like it's written there, no? Like n to the d minus 2 times GDN. Okay, so what does it mean? It means that in dimension 1, it is actually bounded uniformly net. In dimension 2, this quantity, this entropy, is bounded by log n. So it grows slowly, and in dimensions 3 and higher, it grows that n to the power d minus 2. Okay. So if you think about it, the relative entropy of a singleton with respect to this product measure mu rho is of order n to the d. Okay. So that's the largest possible value of this entropy, and here we have a bound for the n to the d minus 2. So we have 2 orders of magnitude with respect to the trivial bound. Okay. And this is somehow it measures the speed at which the stationary state, the empirical measure according to stationary state, converges to this constant mu rho star. Okay, I'm going to present later on today. What do I mean by that? But in principle, it's more or less clear that relative entropy is not exactly a norm, right? Because it doesn't satisfy the axioms of a distance. So the relative entropy is not a distance, it's not even symmetric, so it cannot be cannot really be a distance, but it serves as a measure of the distance between two measures. Okay, so and now I want to explain you how we prove this theorem. Actually, from Gauss inequality is more or less an immediate consequence of two different bounds that now we're going to present. Okay, so the first bound is what we call main lemma in our work with Octavio Meneses, and it's a bound on the integral on the left hand side. Okay, so what we have is that so you may or may not remember that in the relative entropy method there was this entropy production term, this blackboard f function, and this blackboard f function was basically this sum here times lambda. It was the sum here with g equals 1 actually. And well, maybe with g equals lambda. Okay, so that's the type of things that we want to estimate. And you remember I told you that once you have written down Gauss inequality, there are two different paths to follow. Okay, so the first one, in any case of the game, is to estimate the entropy production term in terms of the entropy and in terms of this energy given by the integral of the gas hydrogen. And there you may follow a probabilistic way. Okay, so to treat that entropy production term as an expectation with respect to your Markov chain, or to follow the analytic way. Okay, so say, okay, well, this expectation is just an integral with respect to some density, so with respect to the density of the process at time t. But then just forget that this density is one particular density, and let's try to bound it for any density. So here, what we're doing is to follow the analytic way. Okay, so that function, that sum there, is the entropy production term when you put when you choose the function f as the density of our Markov chain, so ft. And what I'm saying here is that for any density, I have a bound. Okay, so and how is the bound? So this is the energy term. Okay, so this in here is what sometimes called the energy, right? That's it's a quadratic form, so it looks like an energy. And then of course down here you have the entropy. So this is a very recurring subject, no? In this type of theory, in which you have this balance between energy and entropy. Okay. So in Gauss inequality, we have a negative term involving the energy. So we can use that to get bounds. And energy alone is not enough to bound the quantities we're interested in usually. So then you need to have a little bit of entropy as well. Okay, and then there's this energy entropy balance, and so if you do it, if you're well succeed, then the energy entropy balance is good enough, and you win your game, and we get what we want. Okay, so. And here, so you see it it appears this function GDN. It appears the entropy and some constant in front of everything. Okay, so the constant C depends on dimension. There is the in front of the entropy, as should be, there is a gamma -1 because that is the energy entropy balance that I was mentioning. And we have, of course, this quantity has to be has to grow with G, no? So if G is larger, this quantity should be larger. So you have a factor that takes that into account. This prefactor here that takes into account the size of the function G that has to enter into the game. Okay, so so this is what we call main lemma, because is so this inequality is the main technical innovation of our methods, and it's extremely useful. Okay, so it's really what allows us to prove various types of scaling limits for interactive particle systems that were not available before. Okay, so you see this is going to take care of the entropy production term. And so this inequality, and this equality holds for regardless of the parameters. Okay, so the constant C that only depends on dimension, and we have the energy. So there is a cost to perform this this bound, which is given by the energy, and then what you get an extra time, which is the entropy. So if you go to maybe I should, yeah, this is something I should have done here, is that so let me just show you the entropy inequality. No, this is the entropy inequality, and so what I just did is that I bound this term here. So this term here is bounded by the main lemma. Okay, and so the energy cancels with the negative term, which is this gamma n. Remember that gamma n is the Carré-Duchamp associated to the generator. It has two parts. It has a diffusive part, which is exactly what appears in the main lemma, and it has a reaction part. The reaction part I haven't used it yet, and it's very likely that it's going to enter into the second inequality I'm going to present. So in the main lemma, you have now you have this positive term that cancels with the negative term here, and you have the entropy, which is just h of t if you replace the density f by the ft. So there is some Gromwald here that you can do, but this doesn't tell you that the entropy is bounded in time, because if you perform the Gromwald bound now, you will get something that grows exponentially with t. So you need to do something else. But for example, if you are not interested into the stationary state, but you're interested in the behavior of this model at on a finite time window, this is already enough. Okay, because this bound here is going to give you a bound on the entropy, which is sufficiently nice on a sufficiently big time window. Remember that times here is already the macroscopic time, is the time at which evolution happens in the limit. Okay, so let's go now to the second bound that we need to use, which is the so-called log Sobolev inequality. Okay, So remember that I gave you the definition of log Sobolev constant of a Markov chain at some point. No, that's it was basically. So it was 1 minus k in this notation. It was k to 1 over k in this notation. So it's a little bit unfortunate because people use different notations sometimes. But basically the log Sobolev constant is the infimum of the right-hand side divided by the left-hand side of this inequality. So here the non-trivial part is that this log Sobolev constant is bounded uniformly on the parameters of the model. So it's uniformly bounded on the density rho, on the size of the system n. Okay, so what is on the right hand side of this inequality is the Glauber dynamics at infinite temperature. So the measure mu rho n is a product measure. So the log Sobolev constant has something that people sometimes call the tensorization property, which means that the log Sobolev constant of a product, independent product of Markov chains, is actually the infimum of the log Sobolev constant of each of the Markov chains. Okay, so here the measure mu rho is a product measure. So and the Glauber dynamics is just flips each side independent at random with some rate, and the rate at which you do that is chosen in such a way that the measure, the Bernoulli product measure is invariant of parameter rho. And then the fact that this log Sobolev constant is independent of n is more or less clear. It's basically immediate from this tensorization property. Then the fact that it's independent of rho, well, now you have to analyze just a Markov chain on two sides. This is not very difficult. You can do it by hand, basically, and check that effectively. This property is true. Okay, so this log Sobolev inequality is not the most difficult log Sobolev inequality we want to prove. This is an advantage of our setting. This is, so surprisingly, this is it seems to be all very often the case that these driven diffusive systems, they so at some point I told you that these non-equilibrium stationary states are efficient in some way. So of course is far from a proof of efficiency what I'm going to say, but as with we as scientists probably agree that it's a good intuition to have, that is that log Sobolev inequalities in this context are much easier to prove than in the reversible case. So when you have this driven system that puts your systems out of equilibrium, the log Sobolev inequality is easier to prove than when you don't have that. Okay, so this extra randomness that drives your system out of equilibrium helps you a lot in order to prove log Sobolev inequalities. Okay, so now,
sorry, can I ask you? I didn't understand that last point. So here, the proof of log Sobolev is easy because it's a product measure, no?
Now here it's trivial because it's a product measure, but what I'm saying is that here what drives the system out of equilibrium is the reaction term. So
yes,
let's say the equilibrium system is the exclusion process.
Mm-hmm.
Okay, and let's say you want to prove the log Sobolev inequality for the exclusion process. That's difficult. Okay, so it's not trivial at all. The proof is it's really involved. It's, those are two very famous papers. Also, one by Yao, that so it was almost impossible to follow, and then there was there was another paper by Cancrini, Martinelli, and someone else that I forgot. Roberto. Cancrini, Martinelli, and Roberto, and then they also proved the Log-Solev inequality for the exclusion process, and it's so in a much more accessible way, which means that they wrote this almost 50 pages long paper was supposed to be accessible, and it actually is more accessible, but it's still a 50 pages long proof. So it's difficult. But now you put reaction terms, and Log-Solev inequality is completely trivial. Maybe I can go back to this point at the end of the talk, because I probably will have some free time at the end. So then I can explain at this point a little bit better. Okay, so now you see it's you have once we have these two inequalities. So the main lemma bounds the entropy production term by the energy, which is already cancels the negative term in the inequality, and the entropy. And then the Log-Solev inequality bounds the entropy by the reaction part of the energy. So the diffusion part of the energy allows us to use the main lemma, so allow us to estimate the entropy production term by the entropy, by the relative entropy. And then the Log-Solev inequality allows us to bound the relative entropy by the reaction part of the energy. And from this, it's more or less clear what is going to happen. No? So it's there was this lambda in front of the entropy production term. This Log-Solev constant is fixed. I cannot really improve it, because it is what it is. And then if the energy wins over this bound on the entropy production term, we're done. We will have a negative term in front of the entropy, and now the Gromwald lemma will give us the boundedness of the entropy in time. And so now the proof is just basically two lines. So you start with the main lemma, and so you see that we bounded the entropy production term by the energy of the diffusion part plus the entropy, and a constant, which is so this constant term that appears there. So this constant term, when we use the Gromwald inequality, we are going to prove that the entropy is bounded in time, and the bound is going to be given by this constant term here. It's going to be proportional to that. It's going to be this times the divided by whatever constant there is in front of the entropy when you do the Gromwald. So now from the Log-Solev inequality, so what you do is that instead of estimating, so you can bound this in here by the energy, because of the Log-Solev inequality. But instead of bounding this, what you do is that you add and subtract delta times h, just to have something negative to make the Gromwald inequality converge to something finite. Okay, so you do that, and so and we obtain this bound here. So you see from this that if lambda is small enough, this bound here is going to, this expression here is going to be bounded by the energy given by the K-hydrogen. And of course, then you reduce a little bit more your lambda, so you have room to introduce the delta there. Now, remember that our dynamics have a Cx. Okay, so if you look at the K-hydrogen, so maybe I can come back here to here. Here is the expression of the K-hydrogen. Okay, so it has two parts, no? So the first part is the diffusive energy. So this is what I'm calling the diffusive energy. And this is what I'm calling the reaction. So it's not exactly what appears in the Log-Solev inequality, because this guy here is multiplied by Cx. So you want Cx to be bounded below. And if you remember the expression, you see that Cx is bounded below by A minus lambda. By A plus lambda, which is bounded by A minus the absolute value of lambda. Lambda could be negative. Okay, so not the most important part. The only point is that this guy is bounded below, because A and lambda, just because A is strictly between 0 and 1, and lambda is strictly bigger than minus A. So now, so this is the actual bound. So the Dirichlet form that appears in the Log-Solev inequality is bounded by the reaction energy. And there should be something here. Let me see. What I wanted to say is that here I can sneak in the constant Cx, the function Cx. Okay, so from this, you get that H prime is smaller or equal than this, that this in here, and now it's just Grunwald there. So from Grunwald's lemma, we show that at time t, the entropy is bounded by a constant that does not depend on t. Now we send t into infinity, right? Because our Markov chain is irreducible, so it means that the law is converging to the stationary state as t goes to infinity. Okay, so you see how it works. Now we started our process from this measure, this product measure, which we think it could be a good approximation of the stationary state. Then we let the system evolve, and we were able to prove bounds that were uniform in time. And that gives us information about the stationary state. Okay, so with these two ingredients, no, the main lemma and the Log-Solev inequality, we were able to prove this bound on the entropy, which is something that we call the quantitative hydrodynamics. I'm going to explain in a few lines why do I call it like that. Now, let me emphasize some things here which I think are important. So the first thing is that we use the Log-Solev inequality with respect to the measure, to the reference measure. not with respect to the stationary state of the chain. So this is a very interesting point, because the reference measure is something we decide. Okay, so in one hand, it has to be close enough to the stationary state. In the other hand, it has to be explicit enough so we can prove, for example, so we can get information about this, this measure. For example, we can prove the log Sobolev inequality. Okay, so you see that and here somehow you are starting to take advantage, or maybe not take advantage, but to deal with the asymmetry of the chain, because the chain has some it's not reversible with respect to the stationary state, and most of the bounds people have, it's they only use the symmetric part of the dynamics to have bounds. But here we are not using only the symmetric part. Okay, so because of course when you write the Carré-Duchamp, okay, and you write this integral of the Carré-Duchamp with respect to something, that is it's a symmetric form. So it's a quadratic form, which, so in particular is symmetric. So this bilinear operator, when you integrate it, gives you a bilinear form, which is symmetric, and this symmetric bilinear form is associated to a symmetric operator. But when you in the decision, no, in the choice of the reference measure, there is some information about the asymmetric part of the dynamics that you use. In this case here, rho star depends on the non-reversible part of the dynamics. Okay, because if you only use the, let's say, reversible part of the dynamics at the beginning, so to begin with, so if you think about, for example, this model here as a perturbation of the lambda equals 0 case, the lambda equals 0 case has a different invariant measure. So the lambda equals 0 case has rho A as invariant measure. So the density, the stationary density is A, not rho star. And rho star is different from A. So you're already doing something about that. This is even more present when you do the when you use this relative entropy method with a family of moving reference measures, because the family is this family of moving reference measures. It moves, no? Usually you choose it with parameters that solve some equation, and this equation in general is a non-reversible equation. And so and here we're using the log Sobolev inequality with respect to this workable measure. So it's much better situation. Okay. Observe that this doesn't tell you that, for example, that something like the log Sobolev inequality holds true for the stationary state. Okay, because entropy is not good enough to transfer information from the measure from the product measure to the stationary state, although it's good enough to prove scaling limits. Okay, so now let's check that. Okay, let's see how good are these bounds are in order to prove scaling limits for the measure. So now, finally, let me talk about the CLT. So I want to talk about the density fluctuations. Okay, so as I was telling you, so the setup is that you define some random variable, okay, and some family of random variables xn from omega n to some nice Polish space. So what you do is that when you look at fluctuations at the CLT, we have a problem because as you probably already seen in Handy's lectures, for example, for the product measure, the scaling limit is white noise, and white noise has the bad taste to be a distribution. So therefore, you have to work with distributions. Okay, so we're going to define. So the density fluctuations are defined. So what you do is that you define a random distribution and you try to obtain the scaling limit of this random distribution. Okay, so and the random distribution you define is the natural one. So you define it by duality. No, you define its action over well, it's a distribution, so you define its action over some infinity functions, and you define it in a natural way, which is there. No, so we already know that the limit is rho star, so we subtract rho star, and notice that rho star is not the expectation of eta x under the stationary state. Okay, we only know that this is asymptotically the expectation, but not at fixed n. Nevertheless, it's the best guess we have for the expectation, so that's what we subtract. And somehow we hope that this is enough. And the theorem, so what we can prove is that under the stationary state, this random distribution converges in low to Gaussian process X. And again, this holds for lambda small enough. And you see where this lambda comes from. So it comes from the fight of the entropy production term with the log Sobolev constant. So we need the log Sobolev constant to win over the entropy production term, and for that we need to take lambda small enough. So let me identify this process. Okay. So the process X is actually the stationary solution of some SPD. Okay, so finally we are going to the central subject of this workshop, which is SPD. So there is finally an SPD in the node. So this is although it's a simple one because it's linear. So no fancy theory is needed to make sense of this equation. And it's the natural equation, no? It's a reaction diffusion stochastic differential equation. So you have the diffusion term. So probably there is a gamma here. Here, and there is also gamma here. And so we have as usual, since we're looking at fluctuations, you get a linearized PDE. Okay, so this is a linearized PDE around the density rho star. So that's why you get f prime of rho star there. You can check that f prime is negative. No, remember that f was positive at 0 and negative at 1. So it means that when it crosses the axis, it's the derivative is negative. Well, the derivative could be 0. So this is something you have to check, and but it's negative. So and then the noise. Okay, so you have two sources of noise, of course, the diffusion part and the reaction part. Okay, so the reaction part gives both gives an additive noise, but the reaction part, it's a usual standard space-time white noise. There is a constant, there is a variance in front of it. You probably don't remember anymore what the function G rho star is. I define it somewhere. It's not really important for from us today, so I'm not going to enter into more details about it. And the noise, so the noise WT1 is a little bit different because it's a conservative noise. Okay, so the diffusion part of the dynamics, the exclusion part of the dynamics conserves the number of particles, which means that the noise has to be conservative as well. Okay, so if it has to be conservative, it has to have a gradient structure. But then, if you think about a particle can jump in any of the D directions, okay, that means that the actual way in which this noise is constructed is a vectorial white noise. Okay, so what is a vectorial white noise? It's just a vector on which each coordinate is a white noise, and all coordinates are independent. And you take the divergence of that, and that gives you the noise that drives this equation. And there is and also there is, of course, a variance that you have to compute. And I will leave this as an exercise for you. The stationary solution of this PDE can be computed. It's not very difficult because what you do here is that you apply Duhamel formula. So how do you, in general, how do you show existence and uniqueness? How you construct solutions of these linear stochastic evolution equations? It's not very difficult. What you do usually is mild solutions. So mild solution means you use the semigroup of the deterministic part of the PDE to write down Duhamel formula and rewrite this this equation here as an integral in terms of the noises. And then you send it to infinity. You can check that everything converges, and you will have that the process X is going to be the independent sum. So that's what it means, this sum with a circle there, of the integral of the first noise and the integral of the second noise. Okay, so those are the processes X1 and X2. And then you have to compute the variances of this guy. And then you will discover that basically both guys can be written as white noise plus massive free field. So you get, in the end, you can combine everything to get this guy as a sum of a white noise and a massive free field. So this is interesting because although the massive free field as a macroscopic Gaussian process doesn't have long range correlations, in the sense that correlations decay exponentially fast. This exponentially fast decay is in the macroscopic scale, which means that for the microscopic model, you have to look at distance of order n in order to see the decay. So these models, they really have long range correlations. And so if you look at two sides which are neighbors one of the other, and you look at the correlation between them, it's of the same order that the correlation that of two sides which are at distance, let's say 1/100 times n. It is only when you start to grow apart with n that you will see these guys correlating. So and this is a general characteristic of this non-equilibrium stationary state. They have long range correlations. So now that I stated the theorem, I can I can try to give you a quick proof of it. It's I'm going to cheat a little bit in the sense that I'm going to use already proven results which are difficult to get in order to get our final thing. Okay, so first, let me give you some functional analysis stuff. Okay, so you really need to introduce these distributional spaces because unfortunately, the space of distributions is not polished. Okay, so if you want to prove limit theorems, if you want to do probability, it's not a maybe it's not a good idea to look at the directly at the space of distributions because it's not polished. So you can do you have to do something else. Or you can do, for example, tempered distributions or something else. And what it turns out to be very convenient is to do solid spaces. We will see in a moment that why solid spaces are the right call in this particular situation. Okay, so let me just define the law of solid spaces. So it's the usual thing. So solid spaces are just weighted L2 spaces in Fourier, in the Fourier space. Okay, so you take a function in L1 of the or a function on the torus which is integrable, and then you can define the Fourier series of it. No, where in the torus also the Fourier transform is just is actually a series. No, it's defined for integers. So in this case, lattice integers. And well, we do the usual definition. So our torus was it has size 1, so you have to put the 2 pi on the normalization of the trigonometric polynomials, and then you define the norm, the HM norm of a function f as this weighted L2 norm of its Fourier series. Okay, and HM is going to be the completion of C infinity under this norm. So these spaces are nice. Banach are separable. They're actually Hilbert. But usually when you want to do probability, when you want to do probability theory, Banach is Banach separable is enough because it is in Banach spaces that you have some nice theorems. Like, for example, something good about Banach is that Banach allow Oglu theorem works. So it means that the ball is compact in the weak star topology, and that's good for us because it allows to use tightness criteria to prove convergence. And another thing which is nice in Banach spaces is that finite dimensional projections characterize the laws. Right? So you can say, okay, I don't know the law. If you want to describe the law for a random variable in a Banach space, you just take the law of functionals. Anyway, these guys are Hilbert, so everything is even easier and is separable and etc. And so some quick remarks about the fact that these guys are distributions. So this is something that always puzzled me, is that for some reason the delta function and the white noise they belong to the same solid spaces. Okay, so if m is smaller than minus d over 2, then both the delta function and the white noise belong to Hm. Which means that that's basically the correct setup for our problems, because if you see at the definition, what is the definition of the density fluctuation? The definition of density fluctuation is this field here, xn. And you see here that it's just a linear combination of delta functions. Okay, so it belongs to Hm for any m smaller than the other two. And then the limit is also on the same space, so the setup is kind of well posted. And now let's see in dimension 1. So let me give you a quick proof of the CLT in dimension 1. Okay, so the idea is to use this dynamical approach. So you prove convergence at the level of a process, no, a dynamical CLT, no. So you prove you start at the measure. You saw initial measure, and then you prove that at time t, the density fluctuation satisfies a CLT, and then you try to send t to infinity and to make this exchange of limits. In order to do this exchange of limits, so if you remember what we did in the case of the hydrodynamic limit, we need tightness. Okay, so if we can prove that our random processes are tight, then we're okay. Then we were able to do this exchange of limits in a very simple way, because you can just use the stationary state as an initial condition. So let's see how does it go in this case. So the idea is to bound the second moment of xn of f. Okay, so xn of f, so xn is a distribution, xn of f is a real number, so it's a real valued random variable, so we can compute its second moment in principle. And then we use the entropy inequality. Okay, so entropy inequality tells us that the expectation of a function is smaller or equal than the entropy plus the log of the expectation of the exponential of the function. Okay, so you see here why entropy is the right call, because there is this extra log. Okay, because of this extra log that you win when you do the computation, you can estimate the L1 norm of a function. Okay, in principle, the estimate could be very bad, because you need to take expectation now with respect to the exponential of a function. But what happens in our situation is that so this guy has the good taste to be Gaussian, which means that exponentials have finite moments. In particular here, since this xn is going to converge to a Gaussian random variable, we can expect that it has the square has finite exponential moments, at least for constants which are small enough, right? And this is indeed the case. So we do this entropy inequality, and we get this bound here, no? So the entropy is bounded by a constant independent on n in dimension 1, and now you see that we have the log of this integral there. So we want to say that this integral, now this integral is with respect to the product measure. Okay, so this is this xn of f is just a weighted Rademacher sum. And now we have, for that, we have nice bounds, no? You can use here your favorite concentration inequality to prove that this is bounded if alpha is small enough. And here, how small alpha has to be proportional to f, no? Because if you put a larger f, you get a larger random variable. So you multiply f by a constant. This variance has to be multiplied by a constant square. So it's pretty much natural that if you take alpha small enough, what you are going to get is that this is bounded by constant times the infinite norm of f squared. And now with that, we can actually compute the second moment of the norm of xn. And that's the advantage of using solid spaces, because the second norm of the solid, the second moment of the solid norm is easy to compute if you have L2 bounds for your random variables. Okay, and you see well, yes.
So I didn't want to, but do I understand correctly? So the trick with this entropy inequality is that you put sort of all the information that you need about the stationary state, where you don't have much, into this entropy, and then this exponential expectation you have to calculate with this product measure. And of course, product measure you understand much better, and there you have concentration inequalities. Is that correct?
Yeah.
Okay, good. Thanks.
And then you get the bound. Okay, so it depends on m, of course, and here the right call is m bigger than 1/2, no, which is what we expected from the beginning. So you see in this methodology, since we are using these entropy bounds, we cannot expect to have nothing better than second moment, because the exponential moments of powers of Gaussians are not finite. Okay, so the square of the Gaussian is the last guy, which has a finite moment generating function. No? So if you take the Gaussian to the power of any power bigger than 2, it doesn't have exponential moments. So entropy doesn't give us bounds for that. So the best we can hope is L2 bounds. So when Hendrik was explaining things about these Besov spaces, there it was very convenient that random variables were Gaussian and satisfy this sort of sometimes what people call isoperimetric inequalities, which is basically that any higher moments is bounded by the second moment to the right power. And so it means that you can go from L2 bounds to LP bounds of any order if you need it. Here we don't have that. We only have L2 bounds, and we cannot do better than this because our random variables are not Gaussian. Okay, so they are Gaussian with respect to the reference measure nu rho. Well, not Gaussian, but they're Bernoulli, which is basically as good as Gaussian for any purposes. But with respect to the stationary measure, we don't know that. And so we cannot do better than this. So this is why solid norms are very useful here. And in general, norms based on Fourier transforms are very useful. Okay, because it allows us to actually bound the norm with low exponent bounds on moments. Okay, so if you don't have a lot of moments, these solid norms are the way to go, because at the end of the day, in order to make the argument work, the only thing that you need is tightness in some nice Banach space. Okay, if it's h minus n with n equal to 1000, doesn't really matter, because a posteriori you can improve if you want to, because you know that your process converges in a weak topology, but you know that, for example, finite dimensional distributions, they converge in a better topology. So your process as a process converges in a weak topology, but the observables of that you're interested in your process, they usually converge in a better topology because you have more information about them than to the whole process. So, so now the proof is basically is almost done, because so now that we know that second moment is bounded, we basically have tightness, no? Because we know that this gives, just by Markov inequality, now from this we know that the probabilities of balls, of the complements of balls, are small, and these balls, they are compact in the weak topology. And if you want to, and if you don't want to use Banach-Alaoglu, you can also say that the ball in Hm is compact in Hm prime if M prime is smaller than M. So that also works. Since anyway we cannot go all the way to 1/2. If you fix anything below 1/2, you can always find something between this guy and 1/2, and do this argument. Okay, so if you don't like Banach-Alaoglu, there are also simpler arguments. You can use that the ball in Hm is compact in Hm prime for M prime smaller than M. And now you can just repeat what we did for the empirical measure, because we have this theorem. So this is so we wrote some with Otavio Meneses. We wrote some notes with the proof of exactly this theorem, that with respect to so the dynamic CLT. Okay, so the CLT holds for the dynamics, for the dynamical evolution. Okay, so if you start your system with a nice invariant measure, so nice for us means find its entropy with respect to the product measure, then you can show that these density fluctuations evolve with the evolution of this density fluctuation converges to the solution of the stochastic PDE I presented before. And that's it, no? So now what you do is, okay, so the stationary state is a reasonable measure for the it holds into the requirements of the convergence theorem for the dynamical fluctuations. So you can start your system from the stationary state. Then at time t is going to evolve according the SPDE, but at time t is still the stationary state. The measure doesn't change because it's a stationary state. So it means that the stationary state is actually that the density fluctuations with respect to the stationary state, they converge to the stationary solutions of the SPD. And that's the procedure. Okay, so probably we have to make a break at some point, no? So maybe now it's so first I would like to see if the people have some questions. So it's a good moment maybe to ask some questions, and then we make to go for a break.
So can I just, so I understand correctly, so the thing you have, of course, this non-reversible dynamic initially, but the Gaussian fluctuations are given by a reversible dynamic, no?
Yeah.
Okay. And sort of
this is a particularity of one dimension. Okay, so in principle, so
okay.
So we have another result, which is on which you can get a truly non-reversible. Yeah, it's because in this case, so if you put if you start with pure diffusion and pure reaction, this is always going to be reversible, no? If it's linear. But for example, if you have two different substances, now you have room for non-reversible dynamics. Or, for example, if you have a transport term, that of course is going to be non-reversible.
Thanks.
May I also ask a question?
Yes.
I wanted to know if your profile is not if your equilibrium profile is not constant equal to rho star, but it's, well, whatever non-constant, could you still use the same argument? Because I had the impression that your Loxobolev inequality, you could use it because you had this bound with lambda in front. And if you do not have exactly a constant profile, you'd have some discretization error or something in your entropy bounds. So would that still work in that case?
So actually, that's the content of this is exactly what I wanted to say after the break.
Okay.
And so the answer to the question is yes, we can.
Okay.
And after the break, I explain you. At least I will try to explain why.
Okay, thank you.
So, by the way, this is the end of the of my of what I prepared, what I, let's say, formally prepared. So this is the end of my notes. So after the break, I will be glad to answer more questions if you have them, because it's that was exactly the plan. So you were not already make one of the questions I was prepared to answer. So that's what I'm going. That's what I'm going to do after the break. But if people have other questions, please feel free to ask, and then we can have time to discuss. So okay, so let's make a break for some coffee. Okay. So what do you say, Henrik? 5 minutes or 10 minutes? For me, yes. I just need the time for make a coffee and come back.
Perhaps you give people 10 minutes. I think that's nice.
That's good. Okay.
Okay, to see you.
Okay, so now let me answer Benoit's question, which is it's a very good question. So was what so maybe I can go here and record this picture. Okay, so this is a classical example of a derived diffusive system. Is exclusion process in contact with reservoirs. Okay, so this is so exclusion process. With reservoirs. Okay, so in this case here, what happens here is that the hydrodynamic equation is the heat equation. But then you have boundary conditions. right? And these boundary conditions make the system non-stationary, out of equilibrium. So the stationary solutions, no? Is rho of x equals to, so it's alpha plus b minus alpha x, right? So let me see. So at 0 is alpha, at 1 is beta, and it's linear in the middle. So that's it. Okay, so this is the stationary solution of the simple exclusion process with reservoirs. Okay, so this is not spatially uniform. And here, our theorem, so this is actually what we can prove is that so here the small quantity is beta minus alpha. So we can prove something of the form. So let me call this guy rho star as before. And this is going to be smaller than C. So well, you can put the dimensions. So you can imagine that this model is also you can put dimension D in this model too. No, instead of having a segment, you can put a cylinder. Okay, so you put and so in dimension 2 you put so you take it like it's exactly a cylinder. No, so it's let me see if I can find a sheet of paper around here. You have a sheet of paper and you do this, no? So this is a cylinder, and so you can define this model in higher dimensions, and if you do that, what happens is that this is smaller or equal are just the same constants as before. So okay, so I don't need to redefine anything because so we have this bound on the relative enthalpy. But here I have to tell you what is new rho star now and its natural thing. So now at the level of hydrodynamic limits, so you look at the Laplace numbers, and at the level of hydrodynamic limits, the stationary solution is this straight line. So it's not invariant by translations. It's not translation invariant, but it doesn't really matter. And then what you use as a reference measure is this Bernoulli product measure with non-constant density, right? So it's pretty much natural to get to use that as a reference measure, and then you can perform the same. You can have the same theorem, okay? And from this bound, once you approve this a priori bound, you can also obtain the CLT. So the CLT also holds. Okay, I'm not going to. And you were asking. So this one is probably still reversible. Okay, if you look at the corresponding SPDE, because at the level of fluctuation, what is going to happen is that the Dirichlet alpha beta boundary conditions are going to become Dirichlet zero boundary conditions. Okay, so then you still have a symmetry. But you can think this model in so if you go back to this interpretation as a cylinder, no? Right now in the two dimensional cylinder, you have room to make the system go around the cylinder, and in that case, so you can define a particle system on which particles have this tendency to go around the cylinder, and then you will get a truly non-reversible stationary, a truly non-reversible SPDE, and the stationary state is going to be the stationary state of a non-reversible SPDE. So that fact is not essential. It's a little bit a problem of it's more or less it's more like a matrix problem, no? So you have for example, if you look at Lagrange deviations principles, so you have this convex Lagrange deviations functional, and you look at the expansion at the bottom of this guy, and this expansion in order to give you a non-symmetric operator, you need room to make to have to make things whirl around, if you want. Okay, so this is the theorem we can prove. And but Benoit was actually pointing out something which is definitely true, which is that we use the log Sobolev inequality. And in this case here, the log Sobolev inequality is not trivial. It's not like before, because here what we have is only two reservoirs at the boundaries. It's not like in the reaction diffusion model where we have reservoirs everywhere. It turns out that, and this is really surprising, is that you can prove the log Sobolev inequality in this case here. Using comparison principles. So there are these ideas that go back to probably Diaconis and Saloff-Coste, which says that so you have these Dirichlet forms of different Markov chains, and of course, if you can compare the Dirichlet form of a Markov chain with the Dirichlet form of another Markov chain for which you can compute the log Sobolev constant in a trivial way, then your log Sobolev inequality is proved. So actually what happens is that you can check, okay, even if the profile, the density profile is non-constant, that will introduce some correction terms, but even if this is the case, so if you want to create a particle here, what you have to do is to create the particle here and transport it there, right? So we can actually compare the dynamics of the exclusion process with reservoirs at the level of Dirichlet forms with the reaction diffusion dynamics, on which particles are created at each site with a rate that leaves the Bernoulli measure that you are interested in fixed.
Okay, but if you're still considering your previous system, but this time the reaction diffusion rates change with the position.
Yeah.
Would you still be able to say something?
Yes. So it's so the point is that okay. So as was the reference measure is this inhomogeneous measure, right?
Yes.
And then you want to say something about the so you want to prove the log Sobolev inequality for this reference measure, right?
Yeah.
And in principle, so the log Sobolev inequality is not something about Markov chains, no? It's something about the quadratic forms, right? So you have a quadratic form defined on top of a product measure.
Yes.
On top of a given measure, and you want to show that the entropy is bounded by with some constant that hopefully is good enough for your purposes, right? And the idea is that in this particular case, when you do the computations, the quadratic form that comes from the simple exclusion process with reservoirs can be compared with a quadratic form that the only thing that does is Glauber dynamics at each site with a independently with the rates that that comes from that. And now we are done, because for that dynamics is the log Sobolev constant is trivial because it's a product chain. And then the log Sobolev constant is just the infimum over the log Sobolev constants of each one of the coordinates.
But if I'm not wrong, this works because the only place at which you need to use the entropy inequality is for this term with your small parameter lambda, or in this case, beta minus alpha in front.
Yes.
But if you have this non-constant profile, then the Bernoulli product measure with the steady state profile would not be invariant for the rest of the dynamics.
No, yes, you're right, but there are counter terms, so it's not completely. I'm not explaining the whole thing, of course, but the small parameter in this in this situation here is going to be the gradient of the density profile.
Yes.
So because when you do these exchanges, you lose a little bit, no?
Yeah.
But you don't lose too much, because these functions usually are smooth. So this difference is for the 1 over n. So when you do the computations, at the end of the day, you can restate the conditions in terms of this small constant. So the smaller parameter, actually, to be very precise, the smallest parameter is the gradient of the difference between the stationary profile and the stationary profile of the reversible measure associated to the reversible dynamics associated to the product measure. which is not exactly the same, but that's it's more or less of the same order.
Okay, thank you.
So maybe I can state the logs of relative inequality, because I think it's a very interesting result by itself. So I can state it also as a theorem. So this is this was part of the PhD thesis of my PhD student, our PhD student with Patricia Gonzalez, Rodrigo Mariño, which, by the way, defends his thesis in 34 minutes. So it's the following. So let me try to, so there exists a constant k, which depends on epsilon 0, lambda, and gamma, such that for every rho star, so it's 0, 1 to 0, 1, with so let me write this down and then explain you what do I mean by all of this. Okay, so this is the Log-Solev inequality I was referring to. Okay, so it means the following. So let's take a profile. Okay, so let's take a function rho star, which is this static function which is not constant in time, and let's use it as a reference measure. Let's now you want to prove that the entropy of a density with respect to the reference measure is bounded by the energy of one of these, in this case, by the exclusion process with boundaries. Okay, so the first guy there is the part of the dynamic of the exclusion process. As I was telling you, so you have to multiply by n squared because that puts the model into the natural scale, the natural time scale. Okay. So that's the exclusion part, but the exclusion part does not make the system irreducible because the number of particles is conserved. Now you also need to somehow change the number of particles. And how do you do that? You put you put a reservoir. So here I'm putting just one reservoir because actually one or two reservoirs is not very different thing from the point of view of the the log-Solev inequality at least, no? Because maybe two reservoirs will equilibrate the system twice as fast, but from at the level of the log-Solev constant, you're not worried about losing a factor of 2. Because what is really important is that these constants are uniform in n. Okay, so the one reservoir is enough. Not only one reservoir is enough, but the scale at which the reservoir flips does not need to be n squared. It has to be only n. Why is that? Because actually there is something called Robin boundary conditions. So probably when you look at this equation here, no, the hydrodynamic equation, the heat equation, we're used to have Dirichlet boundary conditions and also to have Neumann boundary conditions, right? Neumann is reflecting boundary conditions. For when you have Neumann, the system is not ergodic in the sense that there is more than one stationary solution. No? There's one stationary solution for each total density. But for Dirichlet, no, there is only one. And you can ask what happens if there is something, you can ask if there is a transition between Dirichlet and Neumann boundary conditions. And that's what is called the Robin boundary conditions, which is a mixed boundary condition. You don't fix the density and you don't fix the gradient. You fix a mixture of the two. Okay? And if you want to model that with an interacting particle system, so there is this series of works with so it was Franco Gonzalez Neumann. They had a series of works on which they considered this problem, and they showed that the right way to do it was to put rate, instead of rates alpha and beta, rates alpha over n and beta over n at the reservoirs. And when you do that, is at 1 over n is exactly the point at which you transition from Dirichlet to Neumann. So you do, if you do slower than 1 over n, your equation, your hydrodynamic equation is going to have Neumann boundary conditions. If you put something faster than 1 over n, your hydrodynamic equation will have Dirichlet boundary conditions. So it means that from the point of view of the hydrodynamic profile, putting 1 over n as the reservoir rate is enough to have a macroscopic effect. It's not enough to fix the density, because this is not going to be a Dirichlet boundary condition. In particular, the solution of the hydrodynamic equation is not going to be equal to alpha at 0. It's going to be something else. In the limit, it's going to be alpha because it's going to equilibrate. But it's not going to be alpha a priori. And the evolution is going to converge to alpha. So it moves slowly. So it's not like the Dirichlet boundary conditions. If you start with a profile which does not satisfy Dirichlet boundary conditions at 0, it automatically satisfies the Dirichlet boundary conditions for any later time. So it's reasonable, okay, to weight it by n, because of that, the boundary term. And it turns out that putting a boundary term of order n is already enough in order to prove a log-Solev inequality. And this is what I was trying to tell you about efficiency. So you just put one reservoir with a slow rate of flipping, and that's enough not only to make the system ergodic, but to make the log Sobolev constant of the right order. If you make the boundaries faster, you don't increase the log Sobolev constant. Well, you may increase it a little bit, no, by some constant factor, but it's not true that if you put, for example, n to the cube in the boundaries, you get a better log Sobolev constant. Because somehow what happens at the boundaries, at some point you have to transport it to the rest of the system. So and it's surprising that this is that although the proof is not completely trivial, it's something like a 3 pages proof of this theorem, of this log Sobolev inequality. And if you try to, if you look at the proof of the log Sobolev inequality for the exclusion process without any boundaries, as I told you, it's 30 at least, or maybe 50 pages long paper. So it's for me, it's very interesting that doing this mechanism allows you to prove things easily. No, it's easier to prove things with this mechanism. And of course, this is not, it's not a proof of it's not a mathematical statement, but it's a practical statement. Okay, so if you drive your system out of equilibrium in the right way, the proof of the ergodic properties of the system are going to become easier. Okay, so that's something that I find interesting as a guideline. So this is the situation in the for this process with boundaries. So we can also prove the CLT also under this smallness condition, which seems to be always necessary. It seems to be because of this dynamic phase transition problem that I explained to you before. So here in the symmetric exclusion process, it's easier to think about it. So you have a current from high temperature to low temperature, and if you want to see an anomalous current, it's okay. So some current which is larger or smaller than the average current. Sometimes, so if for currents which are not very different from the original current, the natural way to do it is the obvious way. You know, you move a little bit the boundaries to make the current what you want to do. But if the discharge deviation is larger enough, the efficient way to do it is do something periodic, which is pretty much counterintuitive. So it's not make the current constant in time, but make it periodic in time in such a way that the average current is what you want to observe. So for that reason, I think that these obstructions on the lambda are fundamental. Okay. So I hope this answers your questions of Benoit more or less in a
yes,
very
thank you.
way. Well, I think it's that's basically what I was planning to say. So if you have any other questions, please feel free to ask. And
can I ask one more? So you mentioned this. I mean, this was kind of one of the key points, of course, was this this estimate that you had in the work with Ottavio Meneses, this that you could bound this entropy production by entropy and energy, and you presented this in the context of this reaction diffusion model. But how general is this?
So in the context of hydrodynamic limits, we have a pretty much general in the concept of hydrodynamic limits of interactive particle systems, this lemma is pretty much general. It's
okay.
Okay. There is one important point, which is that we really need the Gaussianity somehow. Okay, so for example, so for independent particles, so for some modification of independent random walks, for example, what you expect is that the invariant measure looks like Poisson, and Poisson and the Poisson random variables, they have the tails are heavier than the Gaussians, and in that case, our methods don't work very well. Thus, it's important that we can bound the square of this guy by this exponential thing. So that's, I will say that's the most important obstruction of our theory. Otherwise, the lemma is pretty general. Whether you can use the lemma in your particular problem is another thing. But it's a pretty much general lemma that allows you to estimate this type of observables in terms of energy and entropy. Whether these observables are the ones that you want to estimate, this is that's the question. And maybe, this is something I wanted to mention, is that we're working in mean field models as on other applications of this methodology. And for mean field models, you can actually bound this entropy production term with probabilistic arguments. Probabilistic arguments are actually better than analytical arguments, because when you look at mean field models, you don't have the spatial structure to help you do analysis. But then the probabilistic, the probability helps you a lot. So you really can see this thing from both points of view, the probability and analysis.
I also have another question, if I may.
Yes, certainly.
The bounds that you have on the relative entropy of the steady state with respect to a product invariant measure, do you expect that these bounds are tight? In the sense that if you normalize by the suitable scaling with n, and you take the limit, you should have a finite object.
Ah, yes. This is something I should have mentioned. This is yes. We believe that these bounds are tight, because if you think about, for example, take this Gaussian limit, this random variable x, which was the white noise plus free field. Okay, so now if you modify it a little bit, so you do some modification of it, you get something which is okay. So in dimension 1, this is absolute continuous with respect to white noise. Okay, so that it means that, so our bound in entropy is tight, because it is tight. But in higher dimensions, if you modify the noise, this Gaussian random variable, and you compute the relative entropy with respect to the modified version of the white noise, you get exactly this rate of decay that we get from our computations. So in that sense, we believe that these bounds are sharp, because the limits satisfy the same bounds.
Okay. Thank you.
If there are no further questions, then let's just perhaps thank Milton again. So I think thank you very much. And yeah, I mean, thanks of course a lot for